In this final talk, I want to spend a bit of time looking in more detail at the shapes of these graphs that we've produced. The so-called exponential rise and exponential fall. They're very common and very important shapes. We'll start with the exponential discharge, or at least this is the graph that we got when we plotted the discharge characteristic of a capacitor. It's also the plot that we got when we plotted the charging up of the inductor, when the current was starting to flow through the inductor. And as we saw, in both cases, the graph obeys this general formula that the voltage is the initial value of the voltage times e to the power of minus t over a time constant. And in the case of charging up a inductor, the time constant was L over R. And in the case of discharging a capacitor, the time constant was R times C. Now, after one time constant, the value of the voltage has dropped by a factor of e to the power of minus 1. Because when t is equal to tc, the time constant, then this would just be e to the power of minus 1. And e to the power of minus 1 is 0.3679. I've just rounded it up to 0.368 on the graph. So, after one time constant, we've dropped to 36.8%. After two time constants, we've dropped down to a factor of e to the power of minus 2 times our initial value. And e to the power of minus 2 is about 13.5%. It's worth noting, however, that if I started off at this point here, which is 0.368, and looked at what happened one time constant after this point here, so assuming that that is my initial value, and asking what the value of voltage will be one time constant after this, the result is pretty much the same. It's still going down to there. It's a characteristic of this shape of the graph. It doesn't matter where you start. After one time constant, you will have dropped to 36.8% of wherever you started. So any two times, which are one time constant apart, will give voltages such that the latter voltage is 36.8% of the former voltage. One point I'll mention here is we quite often try and measure these time constants in the lab. And we don't want to plot the entire curve in the lab to see when it goes down to 36.8% of where it started. So if we're plotting these things in the lab, typically we'll take two readings, approximately one time constant apart. Maybe V1 at some time T1 and V2 at some time T2. And if we want to work out the time constant from these two readings, we would just divide these two equations. So divide our two voltages that we measure, V1 over V2. If we divide the right-hand side of these equations, the V naughts would cancel, just leave us with e to the minus T1 over Tc divided by e to the minus T2 over Tc. Well, that is equal to e to the power of T2 minus T1 over Tc, using the property of exponents that x to the power of a over x to the power of b is x to the power of a minus b. Taking the log of both sides of this just gives me that T2 minus T1 over the time constant is the log of V1 over V2. In other words, the time constant I can calculate as T2 minus T1 divided by the log of V1 over V2. And that's a standard way of measuring the time constant experimentally. Exponential charges do a similar shape. In fact, it is the flip of the shape. it looks identical. If you take 1 minus this shape, you will end up with this shape. So instead of dropping to 36.8%, it's now risen to 63.2%. But what they both have in common is that after one time constant, you have got 63.2% of the distance to where you're eventually going to end up. So we could think of the discharge characteristic as dropping by 63.2% of the way to its final value after every time constant, just as we can think of the charge as rising to 63.2% of its final value after every time constant. And you'll notice that this graph never gets to the final value of V0. That would take an infinite time, just like the discharge characteristic never gets to its final value of 0. There are, however, these useful rules of thumb that can give you a quick approximation of how close you're going to be to that final value. After one time constant, as we've seen, you're 63.2% of the way to the final value. Two time constants, it works out to be 86.5, or more accurately, 86.47% of the way to its final value. After three time constants, you're 95% of the way to its final value. And that's quite a good one, a simple one to remember. Three time constants, you're within 5% of where you're going to end up. It takes 5 time constants to get to about within 1% of where you're going to end up. And after 6 time constants, you're within 0.2% of the final value. But the most useful of these to know is the 63.2% for 1 time constant and the 95% for 3 time constants. Okay, that brings us to the end of this short series of videos. Next time, we'll start having a look at what happens if the voltage source isn't a constant or a pulse, but is a sine wave.